this channel. We are studying class 11 physics in that chapter number 6, work, energy and power. Now today this part 3 video will be containing few very important topics which is related to potential energy, and we will also study the importance of conservative and non-conservative forces. We will study the concept of that, and then we will have to relate how conservative forces are related to potential energy or change in potential energy, right? When we studied kinetic energy, we didn't focus much on what are conservative forces, but here in potential energy we will have to relate the concept of conservative forces and potential energy. Okay, so let us start with the initial concept of potential energy. Now potential energy is the energy stored in a body or a system by virtue of its position or by its configuration, right? An object lying on the roof of a building has potential energy. How we can say that? But if we allow that to fall down, suppose free fall, so it will do some work, it will fall on its own. We can say that we haven't applied any energy, but the gravitational force here is stored in that object, and that will give some energy to do work. Same way, potential energy of water lying in the dams is used to run turbines. So this was potential energy, or the energy stored in a body by virtue of its position. Now let us see few examples that the object have some energy stored in it due to its configuration. So in a toy car which has a wounded spring, that spring also has potential energy, because when we release it, the toy moves, so it does some work. Stretched bow is also a very nice example of potential energy by configuration. And potential energy of compressed spring in a loaded gun is the only reason why the bullet moves forward so fast. So we have seen potential energy by virtue of its position and configuration. Both examples we have seen. There are few types of potential energy that we see in our practical or daily life, that is gravitational potential energy, elastic potential energy and electrostatic potential energy. Right now in this chapter we will be dealing with the first two, gravitational potential energy and elastic. Electrostatic is related to electricity, that will be taken in the next standard. So let us move forward with the first concept of potential energy, that is practical, which is gravitational potential energy. We might have studied this in 9th standard physics also. Now it is the energy possessed by the body by virtue of its position above the surface of the earth. Let us see how it looks like. The figure you see, suppose there is an object of mass m lying on the surface. If we do some work and take it or lift it upward, the g will be the acceleration due to gravity. Note that it will be opposite. Force needed to lift the object, we need to overcome the weight which is acting downward, then and only then we can lift the object upward. So force is equal to mass into gravitational acceleration. Now work done in moving the object in raising through height h. We know the formula of work done. What is work done? It is force into displacement. So it is F into h. Let h be the height by which the object is displaced. So F into h. But what was F? F was m into g. So what is finally W? mg into h. This work done, whatever work we have done against gravity to take the object to a height, this work done is stored in the object as gravitational potential energy U. Okay, so we can finally write U equals to mg h. Okay, and dimensions and unit of the potential energy will be same as kinetic energy, as both are the forms of energy. So dimension and unit of energy will be the same for potential as well. So write on your own. Okay, moving forward, let us now explore the concept of conservative forces. Very important topic, so please take care while watching it and try to find out something more related to conservative forces using reference material and internet as well. Now let us see what is conservative forces. A force is conservative if the work done by the force in displacing a particle from one point to another is independent. Independent means not dependent of the path which is followed by the particle. Thus, it means that this work done or this force which is responsible for doing the work depends on only the end points, means initial and final position. Right? No matter which path you take, it will only depend on the initial and final position. That is why this force is said to be conservative. Examples: gravitational force, electrostatic force, elastic force of a spring are all conservative forces. Now let us see a very nice example. You see, just now we have seen gravitational force acting, and we are taking this object of mass m to a height h. We have three different cases. In all the cases, you see there is a different path by which we are taking the object upward. Right now, in the first case, it is a straight path, right? So what will be the work done? mgh only. Here we are taking this by the path like this, you see, right? It is not straight. Okay, still the work done will be mgh only. And also, if you take a random path like this, initial and final position will only be important in finding the potential energy. That means the work done in moving a body against the gravity is independent of the path taken and depends only on the initial and final position of the body. Hence, gravitational force is an example of conservative force. Okay, so apart from all the examples, we have seen how gravitational force is an example of conservative force. Now, again, let us throw some light on this topic, conservative nature of gravitational force. Now, very carefully, you see this figure. We have thrown an object upward with some initial force. It goes upward, it reaches the maximum height, the velocity becomes zero right now, and then it starts falling. Now, this simple example will prove how gravitational force is conservative. Now, let us focus on the points. Suppose the ball is thrown vertically upward. Now, as it rises, the gravitational force does negative work because initially the velocity was more, so kinetic energy was maximum, and then slowly at the top, the kinetic energy becomes zero. So here the gravitational force is doing negative work by decreasing the kinetic energy. Now the next case, when the object is falling downward, the gravitational force is attracting the object, so it does positive work. Okay, so you can see negative work first half, positive work second half. So can we say that the net work done by the gravitational force during whole trip of this object is zero? And this proves that the gravitational force is a conservative force. Clear? Now, just a simple concept, because we are not interested in non-conservative forces right now in this chapter and this topic. So let us quickly see what are non-conservative forces. If the amount of work done in moving any object against a force from one point to another depends on the path, note that whatever I have underlined, if the work done is depending on the path along which the body is moving, then the forces will be called as non-conservative force, right? And the work done against a non-conservative force along a closed path is also not zero, right? Examples of non-conservative forces: forces of friction, viscosity, etc. are non-conservative forces because they depend on the path. Okay. Now, the next few topics will be very important in understanding the relation between potential energy, how we can represent it in terms of work, how we can represent it in terms of force, right? So, we are relating four different things. First, conservative forces, right? Then, its relation with potential energy. Then, potential energy's relation with work and force. So, four things you have to keep in mind. Okay, now throw a ball in the air. We are just taking a very practical example again. Throw a ball up in the air. You have imparted initial kinetic energy right at the beginning. As the ball moves up, the velocity of the ball is reducing since the force of gravity is acting against it. Try to imagine this situation. You are throwing a ball, you have imparted initial kinetic energy. As the ball is moving upward, velocity is reducing because the gravity is acting against, right? So we can say that force of gravity is doing negative work on the ball. Okay, now let us say that the total work by this journey, this upward journey by gravity is W1. Alright, so work now comes into the picture. The kinetic energy of the ball keeps reducing as it moves up, but we have another form of energy which keeps on increasing. As the kinetic energy is reducing, some another form of energy is increasing. This other form of energy is nothing but potential energy, right? As kinetic decreases, potential increases. Thus, the potential energy at the start is zero, but it keeps on increasing till all kinetic energy is converted to potential energy by the time it reaches the top. So, the gravitational force, this point is very important. Try to understand this. The gravitational force that did negative work on the ball and decreased its kinetic energy has in the process increased the potential energy, right? Thus, negative work has resulted into positive change in potential energy. Three things you have to note. While the ball was moving upward, there was decrease in kinetic energy, and that was due to gravitational force. That means gravitational force is the enemy of kinetic energy. But what happened to potential energy? Due to this gravitational force work, the potential energy was increasing. So this gravitational force, this negative work, was the friend of potential energy, right? So here work done is the resultant of change in potential energy. So work energy theorem, kinetic delta kinetic energy is equal to the work done. Change in kinetic energy is equal to the work done. Okay, so we have seen in mechanical energy, conservation of mechanical energy, that change in potential energy and change in kinetic energy always in any system is zero. So if we replace this W1 instead of KE, the equation will become delta PE plus W1 equals to 0. Now take this delta PE or take this W1 to the another side. What it will give? It will give that change in potential energy is equal to negative of the work done. Why negative? Because gravitational force did the negative work. So here at this end, we have related change in potential energy with work done. Always remember, positive change in potential energy is only due to the negative work done. Okay, so this was the relation between change in potential energy and work done. Okay, now let us see the similar kind of situation, but now we shall relate change in potential energy with force. Okay, now work done is over, but now let us see how change in potential energy is related to force. Conservative force and relation between force and potential energy. Suppose a conservative force F acts on a particle and as a result the particle is displaced. Let us assume that this displacement is delta x. So what is the work done? Delta W equals to F delta x. According to work energy theorem, this delta W is equal to delta K. Work done, change in kinetic energy. So delta K is F delta x, right? But from the law of conservation of mechanical energy, what does it say? That mechanical energy of the system is always constant. And I hope you know about what is mechanical energy. It is the sum of kinetic energy and potential energy. So the change of kinetic and potential is always constant or zero. There is no change, then and only we can say that it is constant. So we can write based on law of conservation of mechanical energy that delta K plus delta U equals to 0. Now if we put delta K as F delta X, so our equation becomes F delta X plus delta U equals to 0. Taking delta U on other side and delta X on the other side, we have F equals to minus delta U upon delta X. Just remove this delta by taking limit x tends to 0. So we can write F equals to minus du by dx. Now see here, this formula is relating force, conservative force, and change in potential energy, right? So you can see, we can conclude thus, in the case of conservative forces, the negative gradient of potential energy will give the force. Okay, so in this slide or in this part we have related conservative force and change in potential energy, that is F equals to minus du by dx. In the previous one, what we have done in the previous part, we just related change in potential energy with work done.